Okay, so today we are going to start working on Chapter 5, Section 2 and 3. And this is all about theorems. We're going to go over 5 theorems for these two sections. And it's really pretty easy. I'm going to make everything very, very simple so we can get through MyLabs Plus. The first two theorems, the remainder theorem and the factor theorem, kind of go together. So let's start with the remainder theorem. Okay, the remainder theorem. If you divide some function by the binomial x minus c, then the remainder is f of c. So let's talk about that and see what actually is going on. I'm going to take this polynomial and divide it by this binomial. But we don't have time to do that because we're in a pandemic. And so forget about doing all of that long division right now. Let's just take a look at the remainder theorem. It says that if you have this binomial x minus 1, I'm going to take the opposite of the number in the binomial, the positive 1, and I'm just going to plug it into the original polynomial wherever I see an x. So I'm going to come up with that, put it in my calculator, and I get the remainder of 6. And that's the remainder theorem. So let's kind of look at some examples. I want to divide this polynomial by this binomial. Okay, I'm not going to do that long division, remember. I'm going to look at my binomial, x plus 2. I'm going to take negative 2 and plug it in wherever I see an x, and put it right into my calculator, and I get a negative 1. So my remainder is negative 1. That's all the remainder theorem is. They're going to give you a binomial, and you choose the negative 2 if they give you a positive 2. Go with the opposite. We're used to that. Plug it into your polynomial. The answer that you get would be the remainder of that nasty long division problem. So how does that go with the factor theorem? Well, if we divide some polynomial function by this binomial, if we get a remainder of 0, that means some important things. It means that that binomial is a factor, and the number that we plug in is going to be an x-intercept. So remember x-intercept, they might use the vocabulary, find the roots, find the zeros, find the x-intercepts, a lot of synonyms. Let's look at this at work. I've been given this polynomial, and I want to know if this binomial is a factor. I'm going to plug in the opposite, negative 1, and wham, when I put it in my calculator, I get 0. So 0 is my remainder. That means that the binomial is a factor, and the number I plugged in is an x-intercept. Let's do it again. Same polynomial. This binomial, I'm going to plug in a 1. I get 4. Ooh, not good. That means my binomial is not a factor, and 1 is not an x-intercept. And that's the factor theorem. The remainder theorem means you plug in the number. The factor theorem means if you get 0, then you have a factor and an x-intercept. The rational zeros theorem means find a list of possible x-intercepts. Again, x-intercepts, roots, zeros. Let's get real. If we want to find x-intercepts, we're going to put the polynomial into our calculator in y sub 1. In y sub 2, we put y equals 0, and then we just intersect and find our x-intercepts. But this is old school, and we have to kind of see what's going on. So, it looks complicated. It's not. We have this polynomial. All we're going to look at is the last number, our constant, they call it p, the first number, our lead coefficient, and they're going to call that q. What they're going to do is get all of the factors of the constant, all of the numbers that go in evenly to 12. Forget about the negative, just look at the 12. And they use plus or minus 1, plus or minus 2, plus or minus 3, 4, not going to use 5, 6, and 12. These are all of the numbers that go into 12 evenly. On the bottom, in the denominator, I need the numbers that go into 3 evenly using plus and minus. So once I get this set up, what I'm going to do is take every number on top and divide it by the 1. That's going to give me all of these numbers. 1 divided by 1, 2 divided by 1, 3 divided by 1, and so on. Then I'm going to take each of these top numbers again and divide it by 3. 1 divided by 3 gives me the 1/3. 2 divided by 3, 2/3. 3 divided by 3 is really 1, and I have that already, so I don't need 3 over 3. So I'll move on. 4 over 3. 6 over 3 is really 2. I have that. I don't need to write it. 12 divided by 3 is 4. I have that. I don't need to write it. So here are the list of possible x-intercepts. Now, what that means is if I put this polynomial in y1, then it hits the x-intercept. Those solutions will be somewhere in this list. Some of these numbers are extra and we don't even need them. But this is the rational zeros theorem, or the rational root theorem. It's just a list of possible x-intercepts. Remember from section 5.1, the degree of a polynomial is your largest exponent. So a degree 2, those are quadratic equations. Degree 3, we called cubic equations, and we always put the exponents in decreasing order. So we're going to use that for the fundamental theorem of algebra. So Carl Friedrich Gauss was born in 1777. And he is credited for the proof of the fundamental theorem of algebra. He did that in 1799. So he was 22 years old when he did this. That's kind of cool. So the fundamental theorem of algebra, we're looking at a quadratic equation, or degree 2. So Gauss says with the fundamental theorem of algebra, if the degree is 2, you have to find 2 solutions. Solutions can be real solutions or complex imaginary solutions. The real solutions are the solutions that hit the x-axis. So in this example, boom, boom, we have 2 solutions and they're both real. So 2 real solutions. So we won't have any imaginary solutions. Okay, this is kind of a cool example. This quadratic touches the x-axis. It touches it, it does not cross it. That means it's a multiplicity of 2, and we have to count it twice. So this is also an example of 2 real and 0 imaginary. Remember, if it crosses, you count it once. If it touches, you count the 0 twice. In this example, the parabola doesn't touch the x-axis at all. That means I have 0 real solutions, which would give me 2 imaginary solutions. The real solutions and the imaginary solutions have to add up to the degree of 2. Let's look at a quadratic. So on this, the quadratic is a degree 3. Gauss says you need 3 solutions. They might be real, they may be imaginary. So in a cubic, 1, 2, 3. I have 3 solutions, and notice the graph crosses the x-axis at 2, 4, and 6. So those are my real zeros. Over here, it crosses at -2, and it touches at 3. If it touches, it's multiplicity 2, and we have to count it twice. So 3 real solutions, 0 imaginary solutions. In this problem, the graph only crosses once. So if I have one real solution, I'm going to have 2 imaginary solutions because my real solutions and my imaginary solutions, the count has to add up to 3. So let's kind of see if we can develop a pattern of this fundamental theorem of algebra. If I have a degree 4, the graph might touch in 4 places, maybe 2. The graph may not touch the x-axis at all. So you'll notice my first option matches the degree. After that, I decrease by 2 every single time in the real zeros column. The imaginary solutions are going to come from the real solutions if I have 4, 0, 2 and 2, 0, and 4. The imaginary solutions start out with 0 and increase by 2. But you'll notice that each set of solutions will add up to the degree of 4. Let's jump over to 7. At degree 7, the real solutions touching the x-axis, it might touch 7 times, it might touch 5, 3, or 1. Notice I'm decreasing by 2. If I have 7 real solutions, I'm not going to have any imaginary 0. 5, 2 imaginary or 2 complex, 4 complex or 6 complex. And you'll notice that they always add up to 7. And that's the fundamental theorem of algebra. This screen really kind of puts it all together. So you can kind of look at this: 6, 4, 2, 0, 0, 2, 4, 6. 5, degree 5, 5, 3, 1, 0, 2, 4. Okay. The last theorem, super easy, is the conjugate pairs theorem. The conjugate pairs theorem is all about the imaginary solutions. And they say imaginary solutions occur in pairs. So if 3 plus I is a solution, 3 minus I is a solution. If 9i is a solution, negative 9i is a solution. Remember, conjugates, one is positive, the other, its conjugate, is negative. If negative 2i is a solution, positive 2i is a solution. So MyLabs Plus or the problem may not state both solutions, but it's understood. If they give you one, you know the other is also a solution. Let's look at a quick example of this. I have a polynomial of degree 3. I have to have 5 solutions, but 1 solution, 2 solution, they only give me 3 solutions. So down here, I know negative 2 is a solution. They gave me 2 plus 4i. I know that 2 minus 4i is also a solution because of the conjugate pairs. They gave me negative 3i. I know positive 3i is going to be a solution. So there, according to Gauss, I do have a degree 5 with 5 solutions. Check. And there we go. We've got our 5 theorems. The remainder theorem. Just plug in f of c and you'll get your remainder. The factor theorem. If the remainder is 0, you've got a factor and an x-intercept. That rational root theorem just lists the factors of the constant over the factors of the lead coefficient and divide. The fundamental theorem of algebra, my favorite, Carl Friedrich Gauss. The degree tells how many solutions, real or imaginary, always add up to the degree. And the conjugate pair solution just means if they give you one complex number, 3 plus 7i, you know 3 minus 7i is also a solution. And that is the end of our